Today's learning target is I can multiply square roots. Now yesterday, remember, we added and subtracted square roots, and one of the things that we said had to be true was they had to be like radicals. So yesterday when we added and subtracted, if we had something like the square root of 2 plus the square root of 3, we couldn't combine those. They're not like radicals. And we compared that to something like, if we had, well, say I had 2 root 2 plus 5 root 3. You couldn't combine those. And that would be similar to 2x plus 5y. They're not the same, so I can't combine them. However, when you multiply with variables and polynomials, suppose we had 2x times 5y. Well, we could say that was equal to 2 times 5 is 10, 10xy. When you multiply, they don't have to be like radicals. And we're going to find that when we multiply square roots, they also do not have to be like, I think I may have called these radicals, but when you multiply square roots, they don't have to be like radicals, just like they don't have to be like variables when you multiply polynomials. So let me show you an example. If you have the square root of 5 times the square root of 20, it really is as easy as saying the square root of 100, because 5 times 20 is 100, and they don't have to be alike. Now, one thing that does have to be alike, the radicands don't have to be alike, but they do have to both be square roots. So if I had the square root of 5 times the cube root of 3, I can't do, we can talk later about something, the ways to simplify these, but now we're not. So this, we get the square root of 100. Now the square root of 100 we know is equal to 10, so we can get an answer of 10 for this problem. Now you can just multiply like I just did, or sometimes what you can do is simplify it. Especially when you have larger numbers. This one wasn't so bad because we know that 100 is a perfect square. But what I could have done was said 20 is the same as 5 times 4. Remember, that's the square root of 5 times the square root of 4. And then I can just multiply. Well, I know the square root of 5 times the square root of 5 is just 5, because when you square a square root, the squaring undoes the square root, and you just get 5. And I know the square root of 4 is 2, because that's a perfect square, so then I end up with 5 times 2 is 10. So you actually can simplify it first. Okay, so on this one, we can just multiply. This is like having a 1 here, so 3 times 1 is 3. Root 6 times root 3 is the square root of 18. And then now I have to stop and think about how I can simplify the square root of 18. I get 9 times 2, and this is 3 times 3. So I can bring a 3 out, times the 3 that's already there, and I get 9 root 2. And that's my answer. Now, when I talk about simplifying first, this is what I mean. I could say 2 times 3 right here. And see, I have the 3's repeat, the factor, so I can bring a 3 out, and I get 9 root 2. So I can think of this as 1 times 3, and since I'm just multiplying, that's the reason why I can group the 3's together and say, and do it that way. Okay, on this problem, and think about what we did if we had 2x times 5x plus 3. With polynomials, remember that we just did the distributive property. So with radicals, we're just going to do the distributive property. So it works the same way. So I'm going to multiply the square root of 5 times the square root of 2, which equals the square root of 10. And then the square root of 5 times 3, which equals 3 times the square root of 5. I can't multiply those and say 15 because the 3 is not underneath a radical sign. Kind of like when I have a 2x times 3. I multiply the 3 by the 2, so I get 6x. but it still remains an x, just like this still remains a 3. So that's my answer, because the square root of 10 cannot be simplified. So I'm done. On this problem, again, I have, I'm going to use the distributive property, just a little bit more complicated. So when I multiply this first one, I'm going to multiply the 3 times 2, and I get 6. The square root of 15 times the square root of 3. 15 times 3 is 45, so I get the square root of 45. Plus, there's nothing in front like a 1, so I have a 3. And 15 times 10 is 150. But now I'm going to have to simplify the square root of 45. This is 9 times 5. 3 times 3. So I can bring out a 3, and I get 18 root 5. Remember, the 3 that I bring out gets multiplied by the 6. Then for the 150, I can do 10 times 15, 5 times 2, 5 times 3. I have a pair of 5s here. So a 5 comes out times the 3 is 15. And then the 2 and the 3 can't come out, so I leave a square root of 6. And that's my final answer. Now, for some of you that would like a shortcut, I can think of this as 5 times 3. So when I simplify this first part, I can see already I'm going to pull a 3 out. So 3 times the 3 I'm going to pull out is 9, times 2 is 18, and I get 18 root 5. And so I save myself a little bit of work. And I do the same thing over here. I think of this as 5 times 2. And when I compare that to this, see the 5 repeats. So I'm going to bring a 5 out, so I get a 15. And then the root 3 and the root 2 stay inside, so I get a root 6. So I like doing that, kind of simplifying it first. I would kind of compare that to doing cross-canceling on a fraction when you're multiplying before you just multiply it all out so your numbers aren't as big. Kind of the same idea that I'm doing here with radicals. All right, on this problem, it's like I have a binomial times a binomial. So think about what I did for this. We just put it in a box. And that's exactly what we're going to do here. So I have 3 plus root 2, negative 5 plus 2 root 2, and fill in the box. 3 times negative 5 is negative 15. 5 times root 2 is 5 root 2. It's negative, so negative 5 root 2. 3 times 2 is 6, so I get 6 root 2. Now be careful on this, because I have the square root of 2 times the square root of 2. Remember, that's this, the square root of 2 squared. Squaring undoes the square root. Anytime you have the square root of 2 times the square root of 2, you get 2. The square root of something times the square root of that same thing just cancels out the square root. So I get a 2, but I already had a 2, so I multiply and I get 4. Now I'm going to combine like terms. Notice I have a negative 15 and a positive 4. So negative 15 plus 4 is negative 11. 6 root 2 minus 5 root 2 is positive 1 root 2. So this is my answer. All right? So multiplying binomials, put it in a box just like we did with polynomials. So here we have negative square root of 5 minus 3, quantity squared. Well, think about what that means. Root 5 minus 3 times root 5 minus 3. So we're going to put it in a box. By the way, you could also FOIL. But most of you, I think, like to organize it in a box. So we have root 5 minus 3 times root 5 minus 3. Square root of 5 times square root of 5. Remember, squaring a square root gives me just a 5. Minus 3 root 5. This box minus 3 root 5. Negative 3 times a negative 3 is a positive 9. Combine like terms. 5 plus 9 is 14. Negative 3 root 5 minus 3 root 5 is a negative 6 root 5. Remember, at this point, we're just adding like terms. We're not multiplying anymore. We're just adding like terms. This is my answer. Okay, next problem. Actually, I think this is the last problem. Again, it's a binomial times a binomial, so we're just going to put it in a box. I have negative 2 root 5 plus root 2 times root 5 plus root 3. So in the first box, I'm going to have a negative 2, and I have a root 5 times a root 5, which gives me 5, remember? So negative 2 times 5 is negative 10. Square root of 5 times square root of 2, remember they don't have to be alike to multiply, so I get the square root of 10. Negative 2 root 5 times a root 3 is negative 2 root 15, because I'm just multiplying 5 times 3. And root 3 times root 2 is root 6. And next we would combine like terms. However, there are no like terms. So my answer is negative 10 plus root 10 minus 2 root 15. That's part of the 2 there. Plus root 6. Even if I attempted to break these down, there would be no factors that would be repeating that could simplify. That is it. It doesn't matter what order you put those in, and you would just have 4 terms in your answer. So you can see how what we did with polynomials can be applied to what we're doing with square roots. You can use the same process, so that should make it so it's really not that difficult.